Ever wonder how AI models learn to chat, write, or even code in a way that feels human? It's not just about data, it's about teaching them what we value. Today, we're diving into a breakthrough that's making AI smarter, more reliable, and better at understanding us. Let's break it down. At the heart of this is AI alignment, the science of making sure models do what we want, not just what they're programmed to do. Think of it like training a dog. You don't just say sit once. You reward the right behavior, correct the wrong ones, and slowly teach them what you expect. But here's the tricky part. How do you teach a model to understand what good looks like? Most AI models today use preference optimization, a method where they learn from paired examples. This answer is better than that one. A popular approach, DPO, direct preference optimization, works by comparing responses and adjusting the model to favor the preferred one. It's efficient, but there's a big problem. DPO treats this like a relative game. It only cares about which response is better, not how good each one actually is. Imagine grading essays by saying, this one is better than that one, without checking if either is actually great. Over time, this creates a weird issue called the squeezing effect, where both the good and bad responses end up with lower confidence. It's like the model is shrinking its options, instead of learning what's truly right. So how do we fix this? Enter MaPPO, maximum posteriori preference optimization. The key idea is simple but powerful. Instead of just comparing responses, MaPPO adds prior knowledge to the mix. Think of it like giving the model a cheat sheet of what's usually considered a good answer. This helps it understand not just which response is better, but how good each one is in a broader context. Here's how it works. While DPO uses a maximum likelihood approach, focusing on the odds of one response being better than another, MaPPO introduces a Bayesian twist. It incorporates a prior belief about rewards, like knowing that most humans prefer clear, concise answers. This helps the model avoid the squeezing effect by keeping both preferred and rejected responses from being overly discounted. It's like having a teacher who not only says this answer is better, but also explains why, so the student learns the real criteria. The results: MaPPO outperforms DPO in critical scenarios. But here's what makes it truly revolutionary. MaPPO stabilizes the learning process by targeting a stationary point, a mathematical sweet spot where the AI's predictions for good and bad choices form a clean, proportional relationship. Unlike other methods, it avoids overcommitting to one option, which can lead to wild errors. Think of it like a pendulum that stops swinging and just hangs straight, balancing confidence with caution. The magic here is in the math. MaPPO uses Lipschitz stability, a concept that ensures its gradient. The math behind how it adjusts decisions changes smoothly. Imagine a car with a built-in speed limit. No matter how hard you press the gas, it won't suddenly rocket off the road. DPO, by contrast, lacks this safety net, leading to unpredictable behavior. Why does this matter? Stable AI means safer tech, whether it's a self-driving car, a medical tool, or a chatbot. MaPPO shows that grounding AI in balance, not just brute force, is the key to trustworthiness. The next time you interact with an AI, remember, behind the scenes, techniques like MaPPO are working hard to keep things reliable, and maybe even a little more human. So what's the takeaway? AI alignment isn't just about making models smarter, it's about making them trustworthy. By blending preference learning with Bayesian reasoning